Hello everyone, welcome to week 5 live session for NPTEL Semiconductor Device Modeling and Simulation course. I am Om Maheshwari and today we will discuss some questions that will help you with your exams as well as your assignments. So let us start. So we are at week 5 and today we will look at some BJT IV relations, Ebers-Moll models, non-idealities in BJTs and metal semiconductor contacts and the current flow and Fermi level pinning. So these are all the concepts that are covered in the lecture videos for week 5. So before solving the assignment, it is recommended that you go through those video lectures, and after that it would be easier for you to attend the assignment. So let's start with some questions. The first question is, calculate the collector current at room temperature, that is 300 Kelvin, and KT is 26 millielectron volts, using Ebers-Moll model for an NPN VJT as shown below, and some parameters for the model are given. So we'll first discuss what is Ebers-Moll model, but before that we need to analyze this circuit first. So here what we have is a NPN BJT, right? So if you see the base NPN BJT will have, this will be N, this will be P, and this will be N. So the base emitter junction is forward bias, and then between the collector emitter there is 0.1 volts. And if you see the base collector junction, that means would be reverse biased. So if I draw this BJT, the base collector, there is forward bias here of 0.628 volts, and between these two terminals you have VCB is plus minus 0.1 volts. So that means this voltage must be 0.528 volts. So this is actually forward bias. This junction is also forward bias. Okay, so attempt this question, then let's solve it together. Okay, so let me first tell you what is the Ebers-Moll model. So let's so that you can attempt the question. Okay, so if we see what is In Ebersmall model, we model a bipolar junction transistor as a series connected back-to-back connected diodes. So we have one diode here and current source, and we have another diode here, the opposite direction, and a current source in the opposite direction. So this terminal is emitter, this terminal is base, this is collector, this terminal is base. So it could be IE, IC, and IB. So this is the Ebersmall model. Now this is, let's say this is I forward, like this. Here are dependent current sources. This is I forward, this is I reverse, and this is alpha F IF, this is alpha R IR, dependent current sources. Okay. So in Ebersmall's model, you can see there are a few conditions. The diode current IF is IF naught e to power q VBE by KT minus 1. Reverse current IR is IR naught second diode's current to q VBC by KT minus 2. And the emitter current IE would be IF minus alpha R IR, and IC would be alpha F IF minus IR. And one more condition is there, it is alpha F IF naught is equals to alpha R IR. So these are the few important conditions that we need to know for solving this question in the Ebersmall's model. Okay, so now let's get back to the question. What we have to find is, we have to find the collector current IC, and we know IF naught, IR naught, and alpha R. So we will use this equation. We know alpha R, IF, and IR. So we can find IC. So IC we know is alpha F IF minus IR, which is alpha F IF naught e to the power q VBE by KT minus 1 minus IR naught e to the power q VBC by KT minus 1. So we know the values. Alpha F is 0.996, these are given in the question. IF naught is 1.25 into 10 to the power minus 16 ampere, and IR naught is 2.5 into 10 to the power minus 16 ampere. So if we substitute these values in this equation of IC, so we'll get IC equals to 0.996 into 1.25 into 10 to the power minus 16 e to the power VBE was given to be 0.68, sorry, 0.628, and VBC we calculated to be 0.528, right? Since this drop was given to be zero point 0.1 volts and this VBE was directly given to be 0.628 volts. So substitute these values. 0.628 kT by Q is given 0.026, 26 millivolt. We can skip the minus one, it will not add any impact. Minus 2.5 into 10 to the power minus 16 to e to the power 0.528 by 0.026. So if I solve this, it will be 3.846 e minus 6 minus 1.649 e minus 7, which will be 3.68 e minus 6, approximately 3.7 into 10 to the power minus 6, and so this is the answer for this question of IC, which is in option B. So please go through this question again once, then we'll move on to the next one. Okay, so I think we can move on to the next question now. So this question is again based on the Ebert-Moll model, and I think you can attempt this one. So please take some time and attempt this one before we solve it together. Okay, so let us attempt this question. So we have to find alpha R for a bipolar junction transition using Ebert's mole model with IF naught is given, IR naught is given, and alpha F is given. So we have seen earlier in Ebert's mole model, alpha F IF naught is alpha R IR naught. So using this, we can find alpha R is alpha F IF naught upon IR naught. This means substitute the values. So please solve this. This is the answer. Okay, so let's go to the next question then. Okay, so I think we can solve this question since nobody's talking anything. Okay, so to reduce early effect, so what is early effect? First, we should know that. So in a bipolar junction transistor, if you remember, emitter, base, and collector. So emitter is highly doped, base and collector are moderately or lightly doped. So when you apply a reverse bias in the, let's say this is NP and N, when you apply a reverse bias in the base collector junction, what happens is this is P side and N side, the reverse bias due to reverse bias, the depletion widths extend, right? So let me call it this dB. So with reverse bias, call it VCB. As VCB increases, the depletion width in the base side dB will increase. And what it will result in? It will result in shortening of the base, and basically if we see IC VCE, the characteristics would look something like this instead of looking like this, right? You will have a non-zero slope here. So that depends on the doping of the sedition base, because the number of charge carriers entering from emitter to the base are also dependent on the electrons that are injected here, are dependent on the base doping, such as say number of electrons is proportional to Ni square by Nb to the power Vbe by Kt, something like this. And this depletion with dB also is inversely proportional to Nb. So as Nb will increase, depletion with dB will decrease, and here as Nb will decrease, the number of ejected electrons will increase. So ideally what we want is, we want here Nb to be lower, because so that we can have more number of electrons, but here we want Nb to be higher so that this depletion with modulation is very low, so that our current does not change with VC CB. Sorry. We don't want our current to change with VCB. So to deal with that, what we can do is we can use the graded base. So what graded base means, we have highly doped emitter here. Then we use some this kind of graded doping here for the base, and collector doping something like this. So what it will help us is, since here based at this near this junction, the base doping is higher than the collector junction, so very little depletion width will extend into the base, and most of the depletion width will extend into the collector side. So this dB will reduce, and here at this junction we already have a lower base doping, so that the injection would be higher, the electrons injecting would be higher. So both of these condition could be satisfied if the base doping is graded something like this. Here it is highly higher Nb, here it is lower Nb base doping. So with base doping using a grade base, we can reduce the early effect without affecting the BJT operation. I hope this is clear to all. Okay, so let's see the next question. Please read this question and try to attempt it. Okay, so let us solve this question. So what we have here is a block of semiconductor So it is situated in dark environment, 10 micrometer in length, so L equal to 10 micrometer. The carrier concentration at this point is 10 to the power 10. We have to find the steady state excess minority carrier concentration at x equal to 5 micrometer, considering diffusion length of the carrier same as the length of the semiconductor. So let's say if it is electrons, LP is same as, sorry, Ln is same as L is 10 micrometer. Okay, so if you know the minority carrier diffusion equation, minority carrier diffusion equation is delta n by del t equals to dn del 2 delta n by del x square minus delta n by tau n plus g after combustion generation. Now we have two conditions here. One is steady state. I'll highlight this equation just for reference, it is very important. Now in steady state, what we have is del of delta n by del t is 0. And second is dark. The dark environment, any generation recombination we can assume to be 0. So in these conditions, our final equation would become dn d2 delta n by del x square minus tan by tau n equals to 0. Now we can rearrange this as d2 delta n by del x square minus delta n by dn tau n is 0. And we know that ln equals to under root dn tau n. So I can replace it delta n by del x square minus delta n upon ln square equals to 0. So delta n of x, solution to this equation would be, considering the solution would be delta n of x is a e to the power minus x upon ln plus b e to the power x upon ln. So this is the general solution to this partial differential equation. So now we know the boundary conditions. Delta n at 0 is given to be fixed at 10 to the power 10, right? It is held at 10 to the power 10. And we can assume delta n at, and this is the diffusion length of carriers same as length of semiconductor. That means all the carriers diffuse and recombine till they reach here. So at L equal to 10, the diffusion, the concentration is 0. So your two boundary condition, delta n 0 is 10 to the power 10 centimeter cube, and second one is delta n at L is 0. So if we put these conditions one by one in this equation, let's put the first condition first. So delta n at 0 equals to 10 to the power 10 equals to a plus b. In the second condition, delta n at L equals to 0 equals to a e to the power minus L by ln, or minus 10 by 10, since L equals to ln equals to 10 micrometer, and put 10 by 10 plus b or 10 by 10 means 0 equals to a e to the power minus 1 plus b power 1, or I can write b equals to minus a e to the power minus 2. And if I put this Moving on is equation 1, equation 2, and this is equation 3. Putting 3 in equation 2, what we'll get is 10 to the power 10 equals to a minus a e to the power minus 2, or 10 to the power 10 is a 1 minus e to the power minus 2, or a is 10 to the power 10 upon 1 minus e to the power minus 2. And similarly we can write b from equation 3 is minus a e to the power minus 2 minus 10 to the power, b is minus 10 to the power 10 e to the power minus 2 upon 1 minus e to the power minus 2, or we can rewrite b as 10 to the power 10 e to the power minus 2 upon 12 minus 2 minus 1 by taking this minus in here. So final, if I put a and b values of a and b in equation 1, delta n of x is 10 to the power 10 on 1 minus e to the power minus 2 e to the power minus x upon ln plus 10 to the power 10 e to the power minus 2 upon e to the power minus 2 minus 1 e to the power minus, sorry, e to the power plus x upon ln. The final equation, but we have to find it delta n at x equals to 5 micrometer, which will be 10 to the power 10 1 minus e to the power minus 2 e to the power minus 5 by 10. Ln is 10 micrometer plus 10 to the power 10 e to the power minus 2 upon e to the power minus 2 minus 1 e to the power 5 by 10. Now we just have to solve this, and if we solve this, what we will get is delta n of 5 will be, this is the answer, which is option C. So we have used, just to recap, we have used magnetic area diffusion equation for solving this question. We had two boundary conditions. First one is that delta n at x equal to 0 is fixed at 10 to the power 10, and second one is this length of semiconductor is equals to the diffusion length. The delta n here would be 0. So the according to magnetic area diffusion equation, we have this, and under the steady state this part equals to 0, and under the dark condition this generation due to some external agents is also equal to 0. This is our final equation, and by rearranging and solving, we got this general solution for it. It's a partial differential equation. Now just by applying the boundary conditions, we got the values of a and b, and then we just have to put x equals to 5 here to find our final answer. That we did here. We found a and b, then by putting the values here and putting x equals to 5, we can find the answer. Okay, so let's see the next question then. Please read this question for a few minutes. Okay, so let's solve this. So we have metal semiconductor junction. So this is the metal's Fermi level. This is the semiconductor. Say wherever its Fermi level lies, let's say somewhere here. So when they come in contact, they will form some bend diagram, something like this, right? So this is VBI that we have to find. EC, EF, V. So if we see the electric field potential here, there's something like this. There will be positive charges. Electrons will go from metal to semiconductor to metal. That's why we get positive charges here. So say electric field looks something like this. So for electric field, let's draw the charge diagram first. So we have some positive charge, let's say plus Q here, due to ND plus. Let's say this is 0 and W. And here in the metal, we will have an impulse of negative charge minus Q rho X. So the corresponding electric field will look something like this. This is the maximum electric field. So this electric field E of X, if we do the Poisson's equation, like we did for the PN junction, this will be the electric field, and the potential integration of electric field into dx. We solve this, we build Q and D W square by 2 epsilon. At 0 voltage, VBI will be this. So we will use this relation to find VBI. So VBI is Q and D W square upon 2 upside. So now all of this is given. Q we know is 1.6 into 10 to the power minus 19, and D is given to be 10 to the power 13. Width is given to be 1 micrometer. So we'll use in centimeters. W square upon 2 into epsilon is 11.7 into 8.854 into 10 to the power minus 14. In centimeter units, we'll take everything. So if we solve this, we will get VBI equals to 0.77 volts, which is the answer. Okay, so next question. The question is, what are the consequences of Fermi level pinning? Option A, the Schottky barrier height will be insensitive to the type of metal. B, Schottky barrier height will behave like a p-n junction. C, Schottky barrier will be ohmic, not rectifying. D, thermoionic emission theory will be have to be replaced by diffusion theory. E, ideality factor of Schottky barrier will decrease. So if you remember in the lecture what is the Fermi level pinning, let's say this is your band diagram. So in Fermi level pinning, let's say this is EF due to let's say some phi m. So if you does not matter if you decrease or your increase your phi m, the Fermi level is always pinned here. So your phi b does not change. It stays the same no matter what phi m metal you have. So this means that the by changing phi m what we are doing is changing different metals, right? So the Schottky barrier height will be insensitive to the type of metal. Schottky barrier height will be fixed, phi b will be fixed, even though you are changing phi m. That means the Schottky barrier height will be insensitive to the type of metal, which is option A. Okay, let's see the next one. Please attempt this. Okay, so let's see this question. Okay, we know potential is the integration of the electric field, that is, we can find VBI is integration of this electric field, or simply area of E versus X. This area is half into this E0 into this width W. This is 1 by 2 into 3.6 into 10 to the power 4 into 0.23 into 10 to the power minus 4. Cancel, and this will come out to be 0.414. Next, if we see the band diagram and doping of 10 to the power 16, so it is if we see this kind of electric field we can only get when we have positive charges here and negative charges at the interface, and this will only happen. This is N-type semiconductor. For N-type semiconductor, we will get this. This will be 5B. This is VBI. This is EC and EF. So we can see from this band diagram that 5B equals to VBI plus EC minus EF. Right. So this is VBI plus KT by Q ln NC by ND. This VBI we have referred to 414, KT by Q 0.026 ln NC is given in question 3.23 into 10 to the power 19, and ND is given in question, this is 10 to the power 16. If we solve this, what we get is 0.414 plus 0.21, which is 0.624. This is 5B. And we have already seen here, this is N-type semiconductor. So answer is option D. 0.62 electron volts is the 5B, and the semiconductor is N-type. Okay, so let's see the next one now. What steps should be taken to establish a reliable ohmic contact? So we know ohmic contact is the one where the electrons can flow on both the sides, and we've seen it in the videos. So generally they have a Schottky contact, but if we dope it very highly, the semiconductor, what will happen is, so this is a normal Schottky contact, but if we dope it very highly, what will happen is we'll have a very thin depletion region here. What would it enable is for electrons to tunnel from here to here or here to here. So this will form an ohmic contact. And this depletion width we can only reduce when we have very high doping. semiconductor, right? So when there is more charge, more potential will drop within less area. That's why we'll have very less depletion width. Doping will increase, WD will decrease. That will make the semiconductor ohmic, the contact ohmic. So what we have to do is we have to dope the semiconductor heavily near the contact. That is the usual practice when we still make the semiconductor contacts in the industry for transistor devices. Okay, so the next question. Given that both HBTs and BJT have an emitter doping of 10 to the power 19 and base doping of 10 to the power 15 for HBT, and the band gap is 1 electron volt, emitter band gap is 1.2 electron volt, determine the enhancement factor in beta for HBT compared to BJT at room temperature. So we know that beta of HBT by beta of BJT is e to the power delta Eg by kT. So this delta Eg, e to the power delta Eg would be 0.2 electron volt by kT 0.026. So if you solve it, it will give you beta HBT by beta BJT to be 2191.42, which is approximately equal to 2192. This is your answer. Shall So the last question for today. In a transistor having finite beta, the forward bias across the base emitter junction is kept constant and the reverse bias across the collector base junction is increased. What will be the effect on the base current? So this is typically what is early effect. We discussed this. Emitter, base and collector. So this is forward bias. And this is reverse bias. NP and N. So when we increase this reverse bias VCB, this depletion width will increase. So VCB will increase, DB will increase. Right? And if DB will increase, what will happen is the neutral base width, let's say WB will decrease. And if WB decreases, what will happen is base current IB will decrease, which is your answer. Base current decreases because there will be lesser area for recombination here. That's what is the major source of base current, right? So with the electrons which inject here are recombined with the holes in the base to give the base current. And with lesser width, the base current will decrease. So that's all for today. We'll continue in the next lecture. Thank you everyone for joining.